Live streaming is on.
I don't hear you, Stan. I don't hear you, Stan. I don't hear you, Stan.
I hope you hear me now.
Now I hear you.
Okay, hello, everybody. I hope you understand that we may have difficulties with technical issues because we are new to the business of broadcasting at that scale. My name is Stan Głazek. I will be moderating this seminar. And today we have Gerald Miller as a speaker. Let me first say something about the technical aspects that are very important. Please keep your mics muted when you're not speaking, and don't let your camera broadcast when you're not speaking, because all these functions influence the quality of broadcasting for everybody because of large number of participants. So let me come to the main issue of today. Gerald Miller will talk about new variable Z, which has applications in all kinds of studies of hadrons. Let me tell you that Jerry is a very well-known physicist who contributed to all aspects of nuclear physics, and he's also contributing to particle phenomenology and even atomic physics. He's interested in proton structure, in QCD, in nuclei, and in effective field theories. His most famous work includes work on cloud-Debye models, on chiral symmetry, and recently on the proton radius. So please welcome Jerry Miller. And Jerry, you can start broadcasting your talk.
Okay, I'm trying to share my screen. Do you see my screen?
I can, yes.
Okay, great. First of all, I want to thank Stan Głazek for originating this seminar series, which I think is a great idea. I want to thank the ILCAC committee for choosing me to be the initial speaker. And I also want to thank Stan Głazek and Johnny Salme for helping me out with the technical issues related to JITC. So I'm talking about this frame-independent spatial coordinate Z tilde, which is very important for light wave functions. I think it connects to deep inelastic scattering, as I'll show you. And there are various other, I think, interesting connections. So I'm going to start first by talking about my motivation. The main motivation for me was curiosity. And I've always been interested in wave functions. In fact, the reason why I got enthusiastic about physics and became a physics major was really learning about probability densities, which I thought was so cool. Anyway, we've seen many talks mainly related to JLab physics and EIC physics, talking about the three-dimensional structure of the proton, which is always presented in terms of transverse spatial. It can be presented in terms of transverse spatial or transverse momentum coordinates, but always a longitudinal momentum coordinate. So I always wondered about what is the third spatial dimension if you're working with light front physics. Now everybody knows about the Bjorkane variable x, which in the parton model is the ratio of the quark K plus to proton P plus. X is K plus over P plus. And the question that I've been asking for a long time is what is the longitudinal spatial variable that's canonically conjugate to X? I was troubled because X has a compact range between 0 and 1. And so what could the spatial variable be? Of course, K plus goes all the way up to P plus. The plus component to the proton momentum. So if you think about it for a few seconds, you realize that a variable which is x minus times p plus, which we call z tilde, Stan Brodsky and I, using a typical light front notation in which the plus or minus refers to x0 plus or minus x3 or p0 plus or minus p3. And we're not the first to think about this. There are probably many others, Stan Gwazek and Hoyer. So we want to think about this just from curiosity. If you have a wave function, what is the spatial extent in terms of just what is it in the longitudinal direction? And the second thing I was struck was by a talk at INT by Martha Constantino, related to current lattice calculations of the quark distribution function Q of x. Now, people have been doing this for a long time, lattice theorists, that is, and in the old way, what they could do was to compute a few moments, which are matrix elements of local operators, and then reconstruct Q of x. But now there's a new way of doing things involving quasi-PDFs in the longitudinal coordinate space. So here we have a typical equation from this paper. You have the Q tilde of x, which is the quasi-distribution, is calculated as a function of the momentum of the proton, here called P. And it's a Fourier transform of a matrix element of an operator, which is familiar to those who study deep inelastic scattering. Here, W is the gauge connection. Later on, we'll go to the light front gauge, and the W will be 1, and the gamma could be whatever relevant operator you like, usually gamma plus for the simplest Q of x function. And so this represents a calculation. Just focus on this term here, this picture here to start with. This is the real part of the function h. It's a function of z, longitudinal coordinate, and you obtain a Fourier transform. And the three curves are coming from three values of the total momentum in terms of 6, 8, and 10. There seems to be convergence. And I would like, once people will do lattice calculations and they'll get the real numbers, but I've always been interested in the question of, can we understand the H, that is this matrix element, in terms of light front wave functions? So I've already done that. By the way, I'll be pleased if you ask questions as we go. I don't mind. I'll be happy to answer them. So let's discuss that a little bit more. Now I go to the the light cone gauge and taking a typical expression for quark distribution. Here I'm calling it FQ of capital X. Capital X can be positive or negative. And this matrix element here has a separation between emission and absorption that is a distance x minus. And as I said, recent lattice calculations compute the matrix element and then get the Fourier transform, do the Fourier transforms to get distributions. Of course, there are still some technical issues with that. They have to be able to go to very large P. Now, so I want to connect to light front wave functions, and gamma plus really is a projection operator onto the plus components of the psi. That psi plus, of course, is the independent component of the quark field operator. And if you insert a complete set of states right over here, and you get matrix elements, and the matrix elements are square of light front the wave functions. There's some index n that describes the intermediate state, and you're summing over all n. And so one can do it, make the calculation term by term in terms of the light front distribution n. And we get the individual component contribution of the Fock space component n to f of x. So, and as I say, there's been a lot of focus lately on coordinate space versions of general parton distributions in transverse coordinate space. But what about the longitudinal canonical variable? And as I said on the previous slide, that the natural variable that is canonically conjugate to the x, the Bjorkane x variable, is z tilde x minus p plus, and its advantage in terms of light front wave functions, which you know are frame independent, z tilde is invariant under Lorentz transformations. So now the standard Fock space representation of light front wave functions are written as schematically here in terms of one x variable, and my notation is that bold-face vectors are vectors in the perp direction. And we have light front wave functions with a bunch of constituents, each one labeled by I. Then you have xi is ki plus over p plus, and k perp 48th constituent, and these are relative coordinates. And so for each of these coordinates, there's canonical three canonical spatial coordinates, z tilde and bi, where z tilde I is p plus xi minus. So this longitudinal spatial variable is a variable for each spatial coordinate. So that means that it's not really, this may remind you about something called the Yaffe time, but this is not the Yaffe time. This is a variable for each spatial coordinate. Now, in the following, I'm going to use z tilde instead of z tilde I because we imagine that one quark is struck in a deep inelastic scattering process or any other scattering process, such as a form factor calculation. So I'm just going to use z tilde for the zi of the struck quark, and the rest is spectators. And then we have the advantage of this canonical variables is that you can do simple Fourier transforms, and you can have two versions. You can have a mixed version of longitudinal space that's over here and transverse momentum, or you can take the light cone wave function in terms of transverse space, B, Fourier transform it, and get the psi n of z tilde and B. Now,
Jerry?
Yes, please.
Hi, Philip, a couple of questions for you. How can x minus p plus be Lorentz invariant? It can only be Lorentz invariant for boosts in the longitudinal direction. I mean, doesn't it mix with transverse components under other boosts?
Well, as I understand it, if you make a purely transverse boost, X minus and P plus are not changed.
You mean that from, if I just start in ordinary X dot P in instant time, you're saying that I can take a subset of that function and get something which is still Lorentz invariant?
That's my belief. But we don't really, let me just say that I'll back up a little bit to think about it later. I'll say it's Lorentz invariant and the transformations in the longitudinal direction. Okay.
Oh, that I'm happy with.
Good.
Jerry, I have another comment or question. This operator Z tilde looks a lot like, if you look at the longitudinal boost generator in the 3 direction in the momentum representation, that's P plus derivative with respect to P plus, which looks an awful lot like what that operator is. I don't know if any comment on that?
No. The whole talk is devoted to giving examples of, I'm getting some background noise here. The whole talk is devoted to examples, and maybe it'll be clearer. I think there are many implications of this, but yes, I've been thinking about things related to that. But you'll see what's covered in the talk will be covered in the talk, and I think there'll be implications for people to think about this thing. As you'll see, you can try this at home. It will be safe to try this at home. Okay, so in the beginning, there were, at least in my own mind, I think Stan Brodsky was sure, but in my own mind, there was a choice of using Z tilde or X minus. And this is related to a question, this choice is related to a question that we've had many discussions about in Lightfront meetings, in ILCAC meetings. Is there a pancake in the infinite momentum frame? Is the proton contracted to a disk in the infinite momentum frame? And here's a nice picture I got from the web. It looks familiar, but I can't quite identify whose it is, but it's I can only guess. Anyway, I stole it from the web, and these blue disks are supposed to be pancakes, and this is a discussion of generalized parton distributions, which yield a 3-dimensional quark structure of the nucleon. So you can have, for elastic scattering, there's something called the transverse quark distribution. You can get the distribution in the variable B-perp, which is a separation between the struck quark and the spectators. And then you can get purely momentum, the usual f of x, which is the quark distribution function. And here you can have a mixed one. But Stan Brodsky has objected to the pancake shape. And my answer is yes. There is a disk or pancake in the infinite momentum frame if you use the X minus variable. And in this talk, I'm going to use the Z tilde variable, which has this Fourier transform. It's canonically conjugate to the X coordinate. But another choice is to use X minus. And in that case, a wave function with the same normalization is written as the square root of P plus over 2 pi times the Fourier transform, explicitly now in X minus times P plus. Okay, now the square root of P plus enters just because of the change of variables and to keep the normalization of these two things the same. If you calculate the density, which is this absolute square of the wave function, then the result is that and this density depends on P plus, but if you take P plus to be infinity, it is a delta function in X minus, the longitudinal distance coordinate. And It is proportional to a delta function. Maybe I should have written that down explicitly, but let me tell you that when you square the wave function, you get a p plus from the factor of p plus from the product of the two square roots, and an exponential in e to the I x minus p plus x, and then another complex conjugate in the other integration variable x prime for the psi p plus star. And that's one of the representations for a delta function. It can be shown. So densities do, in fact, contract to a disk in the infinite momentum frame. But not the wave functions, but the density. But the presence of the p plus is required to get the delta function. And that only occurs if you're taking a density that involves a good operator on the light front. And of course, that means that you're talking about an operator that contains a gamma plus. Now, so in fact, it is correct to think about disks in the infinite momentum frame, and you're talking about a frame-dependent density and a frame-dependent wave function. But I want to, so there is a density, there is a disk. Now, in the rest of the talk, I'm just going to use Z tilde because I'm going to call that the frame-independent variable. Okay, so now I'm going to go back to the frame-independent Z. And sorry, there's a lot of repetition here. And turn to quark distributions. So back to this, for a given Fock space component, there's a contribution psi n of x k squared. And I want to interrogate the distance between absorption and emission of a virtual photon in deep inelastic scattering. So I take this, I Fourier transform each of the two wave functions. I want to express this thing in terms of a distance between the two wave functions, which I'm going to call delta z tilde, and then there's the average position. And you can, what you do is you re-Fourier transform each of these terms, expressing the variables in terms of big Z tilde and delta Z tilde, integrate on Z tilde, and you get some delta functions. And lo and behold, you can obtain a function that I call G sub n, the n being for the given component, and the integral of G sub n of delta Z tilde and x gives you the quark distribution function. So the function G sub n of delta Z tilde and x gives you the contribution to Q sub n of x as a function of the separation. So you can figure out, if you study the G sub n, you can figure out where the contributions to deep inelastic come from in terms of the separation between the two emission and absorption. And the function G tilde, after doing all these Fourier transforms, is another Fourier transform of a very specific kind. You take the Q sub n of y, integrate on the y, and but the Fourier transform depends on delta Z tilde of y minus, delta Z tilde times y minus x is the argument of the cosine function. So we want to, again, I stress that G sub n, which I'll be showing several times in the remainder of the talk, the G sub n of delta Z and x will measure the contribution to quark or anti-quark distributions occurring at a separation. Now, delta, this should be a lowercase, sorry about that. That should be a lowercase delta Z tilde, delta D tilde and x over here are canonically related. One is the position and one is the momentum in dimensionless variables defined by p plus. They're canonically related, and so in fact this is an example of a Wigner distribution. There's been a lot of discussion of Wigner distributions from Cedric and Barbara Pasquini. But this is a new one. It's a longitudinal Wigner distribution, so it's interesting to think about it.
Jerry?
Yeah?
Jerry? If it
Asmita
were,
wants to ask a question. We have a problem with asking question during the speaker presentation, but when I see somebody wanting to ask, I will assume the question is important. Asmita, please say what you wanted to say.
Thank you. I just have a small question. So, Jerry, we have used this variable that you are talking about, the Z tilde, in our work with Stan Brodsky back in 2006 on deeply virtual Compton scattering with Dipankar and Harindranath. So there we saw one effect because the Fourier transform is finite, right? It's from 0 to 1. That had an effect. Do you expect an effect from that finite limit on the Fourier transform when you are using this variable?
Sure, it's right here. We have to integrate from 0 to 1. Yeah, I did read your paper, and we do cite it, or at least we cited it in one version of our paper.
Thank you.
I had it cited, and it's actually in the LaTeX file. It may have been removed on publication because I took out the sentences due to comments by the referee who made me add stuff. But I don't think it's exactly the same. But there are definitely consequences of between 0 and 1, and we'll be talking about that.
There is another question coming from Cedric. Cedric, please ask your question.
okay. Yeah, indeed, delta Z tilde and X are conjugated, Fourier conjugate pairs, but I don't think that we can really say that Gn is a Wigner distribution, because in general, in Wigner distribution, it's always the average position and the average momentum that enter as variables. They are not Fourier conjugate to each other.
Well, okay, this is a new kind of distribution in terms of, well, in Wigner's original paper, I think he was doing things non-relativistically and using relative coordinates. So this is a Wigner distribution. As I said, it's a new kind of Wigner distribution. I think it's fair to call it that, but what's in the name? If you don't like the name, then don't use it. But what it is Gn delta Z tilde and X. Now I have clicked on the proper thing in Jitsi so I can see questions through chat at the same time as I'm giving the talk. So please feel free to ask questions. I hope that the answers I've given so far are okay, but if you can ask again if you want. Any other questions, please feel free. So there's a lot of instructions here on people not seeing it. Try Chrome browser. I hope everything is working for everybody. Are there any other questions?
Jerry, I think you should proceed at this point. If somebody really wants to ask, they will show up in the chat again.
Okay, and I'll be able to see it. So if you want to write your question in chat, I can now see it. Okay, so having this variable, we wanted to see what it does, what can, just to get some a physical insight, and necessarily we chose rather simple wave functions to start with, just to find out what the heck is going on. And so there's a familiar wave function for pseudoscalar mesons, which is the square root of x 1 minus x times this Gaussian form. This is the simplest light front holographic wave function. It's also the wave function of the pion in the NJL model, and probably in many, many other models. It's a massless quark type wave function. It gives us an example of something to do. You can take the Fourier transform, not completely analytically. You really have to do the Fourier transform numerically, and then we're going to square that, take the Fourier transform to get the wave function in Z tilde space, and take the absolute value squared to get the density. You can make an approximate Fourier transform for very large values of B kappa, and you get this expression, which is used to interpret the results. So here I show, as a function of Z tilde, 3 different densities, squares of wave functions for kappa b equal to 0, 1, and 3, and it looks rather nondescript. One thing that puzzled us initially was why for all distances, there's a 0 over here, and that comes because that's the 0 of this cylindrical Bessel function. The cylindrical Bessel function of order 1 vanishes at about 3.8. So this number here, where this is 0, is 7.6. Now, it's a little bit hard to see as we go to large values of z tilde. There's a second bump, and there's a long tail. If you square this J1, you can see that asymptotically the density goes as 1 over z tilde cubed. So that was a surprise. In other words, there is a long tail with a slow power law fall off with large z tilde. So this wave function has some significantly non-zero probability to be non-zero for separations that are way, way larger than the standard sizes of that's related to this wave function. And then the next step is to calculate the g of delta z tilde and x. And so here again, I repeat the wave function. We took the Fourier transform. We calculated the g tilde, the gm. Remember, that's the Fourier transform that involves q sub m. M here refers to meson. You take the quark distribution function and do the Fourier transform, a cosine Fourier transform with delta z and x minus y. And you can get a rather simple closed form expression. You have basically sines divided by delta z tilde. There's a symmetry in terms of x and 1 minus x, which comes from the symmetry over here. And remember that delta z delta z tilde is the distance between absorption and emission. So you see right away that there's a long tail that falls like 1 over delta z. And so the emission and absorption processes can take place at distances which are much larger than the size of the hadron. Here's the picture that we obtain for different values of kappa b. That's the same 3 colors as before. Actually, I don't... Anyway, the point is that you get this simple function, and it's a long, slow fall off, which oscillates with the sines, and it's symmetric. I don't know. So let me come to an intermediate summary. Using what I call the frame-independent variable z tilde gives a way to study light front wave functions in 3 dimensions. The simplest 2-particle wave function has a large spatial longitudinal extent. Deep inelastic scattering can occur at very, very large values of delta z tilde. That's no surprise, I think, especially at low x. Will such effects, this is a game that you can play at home. Will such effects occur in your model? I mean, many of you light front folk have your own model hadron wave functions, and I think it would be kind of fun to look and see what's going on in your wave function. But I have to say that when we were writing the paper, we knew that with that simple wave function that we talked about before, that the quark distribution function is actually unity. So, of course, as usual, this wave function corresponds to some certain scale, and people have made this wave function work to describe the pion structure functions by putting in QCD evolution. But nonetheless, with Q sub m of x equal to 1, we need a more realistic wave function, but would also like to have one that's easily accessible just to figure out what the heck is going on. And we found it convenient to use the wave functions from this model. So this is the title of this paper was Universality of Generalized Parton Distribution in Light Front Holographic QCD. By several authors. Guy will be talking about it, talking about his work next at the next of these seminars. So I'm not going to try to describe this in any deep detail. I'm just going to take it as a given decent model of a wave function to study. The model from the abstract, you read that the model gives you a GPD. It incorporates Reggie behavior at small x, that is, the 1 over x to some power at small x. It's consistent with inclusive counting rules at high x. It gives its claim to give a good, precise description of the nucleon and pion q of x. So I'm going to discuss what this wave function is, because I'm going to use it for the rest of the talk. Now, there are 3 Fox-based components. Tau corresponds to the end of the previous slide. But in this particular case here, tau 2, 3, and 4 is the number of constituents in the Fox-based wave function. The Q sub tau, everything you calculate is a function of tau. And it's written in terms of a function W, which is related to the reparameterization and invariance of the beta function. You can read about that in their paper. And W is explicitly given here. And the interesting thing, which is universal, is that the parameter A, which is 0.531, is the same for the nucleon and for the pion. It's the same variable. And then there's also a kappa variable coming in later, which is a size parameter. And so the GPD, the familiar GPD for the Fox state component 2, 3, or 4 is given by the product of Q of x and an exponential involving T and F of x. So this is the familiar form that people take. And this paper studies this and explains why they do it. And a little bit more advertising for that paper. They have calculated the U-quark distribution and the D-quark distribution for x times Q of x as a function of x in this log scale. And somewhere in there, the solid line is their curves. And this is various modern parameterizations that you can find in the literature. And they get what would seem to be a rather good description. I should say, they have this is at a momentum scale of 10 GeV squared. The starting scale, the scale at which the light front wave function is defined, is about 1 GeV. And here's the same kind of plot, xq of x, as a function of x for the pion. And again, a rather good distribution in terms of the experimental data is obtained. So this is a realistic model. It's a realistic model, but it has a neat enough and compact enough mathematical structure so that it's easy to take numerically to Fourier transforms. So the first thing I want to show you is the wave function. And I'm going to compare it. I just take one component, not to bury you with pictures. Take tau equal to 2, so that I can compare it with what I call the first HLF QCD wave function. That's a lot of initials. So in blue is the wave function that I started with. In red is the function, the light front wave function that corresponds to tau equal to 2. And I thought a picture would be better than an equation, but the interesting thing here is that there's this wiggles of kind of structure in coordinate space. And this is, I didn't do the labeling. This is labeled as a function of x over here. This is not z tilde. So going back to Asmita's question, in this picture, the x goes from 0 to 1. And I'm showing the two different wave functions for different values of separation in dimensionless units. And the key thing is that with this new wave function, the second wave function in this talk that incorporates the Reggie behavior, we have a structure at very low x that's built in here. And that will cause wiggles in various things that we calculate and show you later on. Are there any questions? I'm looking for chat. Okay, so I need another sip of water. Okay, I'm now going to start talking about the Z tilde dependence. I remember that 2, 3, 4 is the number of constituents. I'm showing you the light function, wave function squared for tau equal to 2 at different values of B. These numbers on this plot with these different curves refer to different values of B, and the density is a function of B for different values of B is a function of Z tilde. And the numbers refer to B in units of 1 over GeV. And again, it sort of looks like a Gaussian in any case, but there's this region over here in which you can't see. But if you blow it up and go to large Z and multiply by Z tilde to the 1.6, the wave functions, the densities rather, have a universal fall off, at least in terms of universal as far as 2, 3, and 4 go. There's a dependence. Each one has a fall off of 1 over Z tilde to the 1.6, which is a very slow fall off indeed. And the oscillations are occurring as a result of that structure in the wave function. And that has wiggles. There are more wiggles for two components than for 3 and for 4. But the thing is that you have a very slow fall off. So there's a very, very long tail in the Z tilde space. So the wave functions, which we think of hadrons having typical size characterized by 1 Fermi, there's this long tail, so there's a non-zero or significant probability that the constituents can be well separated in the longitudinal direction, which I think is amazing. And maybe that's true and maybe that's not. It's a consequence of this wave function. The wave function is well constrained by lots of data, but it's something to explore in terms of future physics, in terms of trying to understand what, ultimately we'll be interpreting lattice calculations. We want to understand the physics behind the wave functions that come out of lattice calculations. Are there any questions? I see not. Okay, I'm going to go on. And again, using the same paper, the 2, 3, and 4 is the number of constituents. And I'm plotting here G sub tau of delta Z tilde and 0 for 2, 3, and 4. Remember what the meaning of this thing is. This is just G tilde is this particular Fourier transform, which gives you the contribution as a function of delta Z tilde to Q sub n. And I'm showing it for 2, 3, and 4. The proton, maybe I didn't say this before, proton is a linear combination with approximate, I forget the exact ratio of the two components. There's 3 and 4. That corresponds to the proton, which has to have at least 3 constituents. And then there's a component with 4 of an almost equal probability. And the G tildes look like this. And again, they seem to fall off. Again, there's a huge tail in delta Z tilde. It goes on for a large distance. Remember that the delta Z tilde refers to the distance between absorption and emission at large delta Z. Now here I make a comparison with which is about something which is almost but not quite the same thing as calculated on the lattice. My function, our function G, is a symmetric function of delta Z tilde, so I don't show the negative values, which are symmetric, as in this lattice calculation of the same thing. Although this is for U minus D, and I haven't done that here. I just realized that I could make this comparison in preparing this talk. Now, the dashed curves, these dashed vertical lines correspond to the same position in the lab frame. If I go to the lab frame where delta Z tilde is proportional to X minus times the mass of the proton, this dashed line over here corresponds to this dashed line here. And if you look at these curves, there's either 3 or 4 for tau is down by a factor of about 20%. And for the same distance, this is down by about a factor of 2. So you can qualitatively see that this G tilde, this G tau, which is comparable to this H, this one is falling off much more slowly. But it's too soon to assert that there's a difference between the lattice calculation and this model, because the scale of the wave functions are different. And that's something that has to be worked out. To make a better comparison, one has to evaluate this at the wave functions at the same scale, and or the matrix elements at the same scale, and this has not been done. But in any case, there is a new feature that there are significant contributions at large delta Z. Finally, I want to sort of make a correction. What we calculated in the paper was correct, but it wasn't the best thing to calculate. People who do, like Burkhardt, who do the average, who calculate things in transverse coordinate space, have focused attention on the average value of B squared. And the way that everybody else does it is to calculate the expectation value times the square of the wave function, in which the wave function is normalized to 1. So this is a different quantity that was plotted in the paper. But one can just get the average separation B squared in the trend. That's a separation in the transverse direction. One can get that average separation as a function of Z tilde, and show you for tau equal to 3 in red, tau equal to 2 in blue, B squared of Z tilde as a function of Z tilde. And in both cases, there is a new and unexpected feature, that there's this long tail in this spatial variable. So I come to the last slide and the summary. What we have what we call a frame-independent longitudinal spatial variable. That's the Z tilde. It's X minus times P plus. In the two models that we have, the squares of wave functions have a long tail in Z tilde. The distance in these two models, only two models, the distance between absorption and emission of virtual photons in deep inelastic scattering can be very large, and it's especially so at small x. Now, it's my hope that the function G tilde, G of delta Z tilde and X can serve as a bridge between light front wave functions and lattice calculations of GPDs. And so finally, since for this audience, I can ask the question, what is the Z tilde dependence of your wave functions, since you all have so many? Thank you very much for your attention.
Thank you, Jerry. Thank you very much. If anybody has a question, please write in chat that you want to ask. If I can be helpful, I will. Okay, James, go ahead.
Very nice, Jerry. Very nice presentation. I think this is a particularly interesting variable, and I think your last bullet here is a challenge that we should take very seriously and produce the z tilde dependence of our some of our light front wave functions, which
Yes.
which I believe will be quite dramatically different from the ones you've showed today, for a very simple reason. And that is that when we incorporate a longitudinal confining term in our Hamiltonian, we can expect the long distance behavior to be significantly different. Just a simple hand waving statement is enough to say that. But how quantitatively different, that's another very interesting question which we should address.
Yeah, I think this is, I agree with what you said, especially where you said you like to talk. But I've been studying your papers. In fact, very much. I think that it is very important to include, what you call the longitudinal potential V sub L in holographic type calculations. This is really necessary, and I'm in the process of preparing a paper on understanding Bloom-Gilman duality, and taking that physics into account is crucial to get Bloom-Gilman duality. So I see Guy wants to talk, and there's also a question from Philip Mannheim. So I don't know who was first. Dan, you're the moderator.
Yeah, I would say that now it's time for Philip.
Okay. All right. Good morning. Jerry, I calculated your function z tilde. It is indeed invariant under a boost in the longitudinal boost. It's a true Lorentz invariant. However, it's not invariant under a boost that mixes into the transverse.
Yes, okay.
So it's okay. It's interesting that there is actually a quantity which is Lorentz invariant under a longitudinal boost. Now, a couple of other comments. Well, first of all, a comment. It sounds a little bit about like W spin. I don't know if you remember back to SU6W when people were trying to make SU6 more covariant, and they introduced a W spin back in the 1960s. That was Lipkin and Meshkov, I think. Lipkin and Meshkov. It may be related, because I know they were looking to make the old SU6 model, which included just three-dimensional rotations, was to try to make it a boost invariant. So it may be related.
Okay.
The other question.
Let me say, yeah, I'll read the paper and find out what they said. I was only a graduate student.
Well, I'm remembering it from the time I was a graduate student too. But okay. I was actually, the W, by the way, stands for Weizmann, and I was at the Weizmann Institute doing my doctorate.
Cool, okay.
Now, the other thing I wanted to note on, you said that tilde z is a canonical variable. What's it canonical to?
X minus, it's canonical to...
is there some quantity that it commutes with and gives a delta function?
Yes. Oh,
good.
Yes, it's IH bar. It's just as the usual x. The x coordinate, going back to non-relativistic, the x and p sub x have a commutation relation, and the x minus is conjugate to the k plus, and the p plus factors are put in here to make things dimensionless.
Oh, okay.
Remember that in the life front, x minus is space. Yeah.
It's really just the canonical nature of x minus itself.
Exactly.
Ah, okay. I thought there might be some other thing related associated with the p minus p plus. All right, thank you.
You can do things in life. I love about the light front, I love the fact that it's really just regular quantum mechanics, except except that it's like in the infinite momentum frame. There was a question from Guy or Guy.
Let me see. Jerry.
Yes.
Yes, hello. Well, very nice talk. Thank you very much.
Thank you.
I am also concerned by the long range, of the wave function. So my question goes along James Vary, and it is how to include quark masses into this wave function you call the number 2, I imagine. Well, the first one was a very naive one because just
correct.
holographicity has one variable, so it's not easy to incorporate quark masses. So you have to extend the model somehow. But
I agree.
Yeah. So in this model based on the extension, which is really constrained by the beta function structure, or if you want the Veneziano form. There is it's expressed in terms of the Ricci trajectory, so that's extremely convenient. And in the expression you show, this corresponds to 0 quark masses indeed. So how quark masses do enter the game is in the intercept of the Ricci slope. So we have published several papers with including this, because of course it's extremely important if your current is not of a row meson, but say from phi, then the shift is quite important. But even with a U and D quark masses, that means for the row meson, there is a shift into this intercept, and this is very simple to introduce into your computation, I guess. So it would be very nice to change slightly the Ricci intercept and see what is the effect in the range.
Oh yes, that's a good suggestion. We do have one calculation. I think in general, putting in the mass is something to some extent still an unsolved subject. I think James's prescription is a good one for large masses, large quark masses. I think work needs to be done on that. And we do have one calculation in the paper in which we use one of the prescriptions that's in the review articles and in one of the numerous papers that you have, in which you put in the simple wave function, you put in e to the minus a factor of e to the minus m squared over x1 minus x, something like that.
Yes.
And we have a calculation in which we did that calculation. It's in the paper, and it also it's a different thing. It's in the paper. Maybe I should have discussed it, but I'm not happy with the way that came out, so I didn't talk about it in this talk. I think more work needs to be done. We have to get a better wave. We need to have a better wave equation for a better holographic wave equation to obtain these wave functions if you want to go back to first principles. And that's really all I want to say. It's an unsolved problem in my mind. And,
right. Probably there is still exploration to do.
Correct.
To show
yes,
what is
definitely.
Correct.
Thank you.
But,
yes,
but indeed, one has to be very careful when one introduces the quark masses, because one can lose the power counting rules. So this when you incorporate this in shifting the Ricci intercept, count inclusive and exclusive counting rules are preserved. So this is an important point to look at as well.
Yes, thank you for the help. Yes, I agree. I think this is really, only the beginning. I think, first of all, I think it's interesting if you have a wave function to see what's going on in that wave function. But it's no surprise in deep inelastic scattering that the photon breaks up into a quark-anti-quark pair long before it hits the target.
Yes.
So this idea includes that. So it's not, that's not exactly news. What's news to me is that you get this change in the wave function. And the other thing is, I think going back to this early slide here, this thing is what lattice gauge theorists are now calculating, and it's a way to make contact between lattice calculations and light front wave functions. In the end, we hope to see today when the lattice calculations really become more and more definitive. They're almost there. And then we want to understand what that means in terms of light front wave functions. How many constituents really matter? Is it 3, 4, 5, or 6 for the proton? Question of real physics.
Probability of
Light,
your ansatz.
Do I have, sorry, I missed because of the word. Do I have a probability of what about my ansatz?
The valence probability of your ansatz. Did you have
I forgot the number.
Calculated?
No, it's in the model. What that paper did was to take a linear combination of Q3 and Q4. I think it was a 2-to-1 or the 3-quark component. I call it 3 quarks. The tau equal to 3 component. Let me go back here to this. The tau equal to the proton was made out of tau of 3 and 4. And I think it was 2/3 3 and 1/3 4, and that was determined by fitting it to data, and that's in the Fizrev letter. To me, this is a very interesting thing that they're able to get such a good fit with this. Because you might think that there's an interference between components, that you wouldn't just add squares of wave functions. If there could be interference between Fox-based components in general if things are complicated enough. And the fact that you don't need this interference is very significant. And to me, I've written another paper in which I use this wave function to, I think these wave functions justify the Strickman-Frankfurt approach to understanding the EMC effect in terms of modification of point-like configurations. I think this is in a separate paper that the tau equal to 4 corresponds to a point-like configuration in the proton. And that's in a separate paper that I put out in July.
Thank you.
Cedric.
Thanks for the nice talk. So, would you agree with me that what you call delta Z tilde is essentially proportional to the skewness variable in GPD's time plus? If you look at the definition. And that's interesting because
no, I don't agree.
Well, you define delta Z, capital Z tilde and delta Z tilde.
Yeah. Okay.
So how I understand things that capital Z tilde is Fourier conjugate to the X in DIS.
Yes. That's the way I understand it. Yes. The skewness, I'm not sure. I haven't thought about it that way, so I can't give you an immediate answer. Maybe I should think of it that way. I'll think about it that way, and you're welcome to as well. And tell me what you think. I'll be happy to listen as usual.
Okay, because that would be interesting because by a Lorentz transformation, we can go to the Drell-Yan, where you have the same mass for the initial and the final state. In which case, you can find a Lorentz transformation that sets delta Z tilde to 0.
Oh.
Oh, interesting. I guess that's true.
Okay, I have to think about it.
You can get.
Not if it's
Let
less.
me, hello, let me interrupt for a moment. We should say that the standard discussion time is over. Anybody who is done with the formal part of the seminar can turn off, but we have about an hour, half an hour of a free discussion that everybody can still be in. So formally the talk is over, but there is time for discussion with the speaker. And I'm interrupting you because Philip Mannheim has another comment, and he was waiting patiently for many minutes to get to the microphone. Philip?
Yes, okay. Am I live?
Yes.
Yeah.
Oh, okay, good. Jerry, you said a very interesting thing about using this Z tilde is something like you can use non-relativistic ideas. So I just wanted to comment on something I wrote up recently in PhysRev D, and that Stan Brodsky, Peter Loudon, and I wrote up in a big physics report. And the question was, what's the non-relativistic limit of light cone physics? And you know that you can write P0 is P plus plus P minus. That's just the definition. That's for the momentum. But what I was able to show was that also holds for the operators, that the momentum zero operator is equal to the momentum plus the momentum minus as operator identities. Now, the next thing I asked was, what does it mean to be non-relativistic? And the answer was, it means that P3 is small, the usual component, and that means that P plus is equal to P minus. And so the non-relativistic limit of a light cone Schrodinger equation is the limit in which P plus, the variable, not the operator, becomes equal to P minus. And I think that was the point we identified.
Yeah, that's very interesting. I wasn't aware of the paper, but thank you for telling me about it. But what you say sounds eminently reasonable. I did it about 20 years ago. I did some calculations in which I used light front ideas to derive nuclear physics, standard things in nuclear physics, and it may be relevant to say that to do the calculation of the nuclear wave functions, I minimized P minus subject to the constraint that P plus was equal to P minus.
Yes.
And of course, that was a fancy way of saying that I did a variational principle on the Hamiltonian.
No, that's very good, because what I was saying was the non-relativistic limit is not P minus goes to zero.
Right.
It's P minus goes to P plus.
Correct. I agree. P minus goes to zero means infinite P3.
That's infinite momentum. Yeah.
Right.
Any questions? Comments?
Xing Bao.
Zhao would like to talk.
Good.
Xingbo, Zhao?
Hello, can you hear me?
Yes.
Yeah.
Yeah. So I have a very nice talk. I have a very naive question. So, so basically, the observable, the quantity you propose as a function of z, how it is supposed to be measured experimentally?
Wow. Yeah. It's only indirect. Well, first of all, let's see. I guess what I'm looking for. Is here. Of course, you measure not just one flux space component at a time, but you can get to some of those q sub n of y. Of course, I've suppressed the q squared dependence. If you measure q sub n of y at a for a complete set of values between 0 and 1, you could do an inverse Fourier transform, I guess. Well, if you measure q sub n of y, you can do this calculation and learn about what is delta z experimentally as a function of x and q squared. So that's the only way I see, because really it's a variable in the wave function. It's like asking in the hydrogen atom, how could you measure the x component or the z component of how can you directly measure in the hydrogen atom? Actually, there's ways similar. Yeah, I think the best way to say it is here. I could think more about your question. It's a good question.
Oh, okay, thank you. Yeah, thank you. I'll also think about it.
James?
Yeah, just to comment on that discussion. Traditionally, when we ask the question about coordinate space distributions, we think in terms of measuring a form factor, which would bring us to the question of longitudinal momentum transfer, form factors, and maybe there's a connection there. I mean, we're so used to think of measuring everything in the transverse form factors with the transverse plane momentum transfer, but here we might be challenged to think about a different form factor and its behavior as momentum transfer goes to 0.
Yeah, doing that would require, I think, a step forward. We use the Drell-Yan frame and take, the form factors of Fourier transforms in the perp variable, and the Drell-Yan frame is the one in which Q plus, the plus component of the momentum transfer is 0. And that simplifies the calculations of form factors. Now, if I want to avoid Q plus being equal to 0, then it becomes related to the skewness, but you have to deal with the dynamical nature of the boosts in the longitudinal direction.
Mm-hmm.
So it would be cool to eventually do that and show that you get the same results. But nobody has been bold enough to try that I know of.
Oh, is there any other question or comment? Yang Li, please speak.
Okay, thank you very much, Dr. Miller, for the nice talk. I just want to mention that and you and Dr. Dieter mentioned the uncertainty on obtaining move functions in QCD. I was wondering if you consider move functions from QED, where we have much more certainty, like the wave function of a photon, electron, even positronium as for the bouncy system.
Yeah, I haven't. That's a good suggestion. A while back, I wrote a paper in which I took I used QED. This is published in PhysRevD. I used QED to calculate GPDs. I wanted to understand, in terms of the physical electron has an electron photon component. And so I calculated in QED various GPDs, in the full menu that people have to see what was, just so that I could understand GPDs. I think the same could be done for this variable as well. It's another realistic example. So I think that's a good suggestion, which could in fact you can carry that out. What is the longitudinal dependence of the light front wave function? Which the only way to get wave functions, as we all, I think everybody in our community would say, the only way to get real wave functions is to use the light front formalism, and so you can do that in QED, and in there, you know, you're really dealing with nature.
Right.
You really got it.
At least perceptively, yes.
Well, yeah.
There's another comment, you know, along the line with your discussion with Dr. Very's suggestion that the form factor. I think traditionally we do form factor, as Dr. Very pointed out, we calculate form factor in the bright frame, so that you only the calculation only involves this transverse momentum transfer.
Right.
You can call it delta to distinguish with this k, the momentum, transverse momentum. But I think this is not the only choice. In fact, you don't have, you don't even have to make a choice. In principle, you can do you can develop a formulation with form factor using boost invariant variables. If you do that, like I just did, I think you can find out that, just like the impact parameter B, which will be conjugated to this momentum insertion delta, you will find out that this Z you introduce is conjugated to this momentum fraction variable, similar to delta, the boost invariant momentum. I think that's something that you can take a look at.
Yeah, I will. What's the reference? What's the archive number?
I think I can send you one of the papers that I did with Dr. in 2018. I think there you really have a nice unification of three-dimensional with the variable you have.
Very good. Please send me the reference. My email is easy. It's Miller.
Sure. Yeah. I think we have we collaborate on paper together, so I should know your email.
Sorry, I don't recognize the voice. I don't see your face. Great. So send it to me. I'll look at it for sure.
Thank you.
Hello. Any further volunteers to say something?
Yes, I have a raised hand.
Okay.
Hi. So I just was listening to the last comment. That was a very interesting suggestion to look at this QED wave functions. Actually, in our 2006 paper, we did that. So we have studied this QED wave function, and we studied it in this Z tilde. We called it sigma space. But one thing that is quite interesting is that in that study, we also did a Fourier transform of the deeply virtual Compton scattering amplitude. James Berry was also a part of that study. And we have introduced this longitudinal space component there as conjugate to the skewness variable.
So it's a different variable than what I'm talking about.
Later we also introduced it for the wave function in the same way as you have done for the QED wave function. But what I was saying is that when we did the study, we actually saw some interesting effect coming from the finite size of that Fourier integral, not finite size, but the finite limit, 0 to 1. We found some diffraction-like pattern in sigma space, which is the same as your Z tilde.
Sorry, I didn't hear the last sentence. You found something in sigma space. What was that?
Yes, some distinct maxima and minima.
Yeah. Well, we have, we have lots of wiggles.
Yeah, so something similar we found, and we also tried to explain it from physics point of view. for deeply virtual compound scattering. So we had really compared this findings with some optical slit experiment, like in diffraction.
Oh, interesting.
And, yeah, so.
Yeah, thank you for telling me about this reference. This helps. I read the paper, but now I can go back with more understanding.
Yeah, we have actually 2 papers at the time. So the author list includes Stan Brodsky, James Wary, Harindranath Dipankar, and myself. One published in Physics Letters B and one in Physical Review D. And there we mostly studied deeply virtual compound scattering, but for an electron in QED for a simple state.
Very interesting. I'll be sure to look at that. Thank you.
Thank you.
Welcome to Prudential. Please note calls are recorded to help us improve service. Thank you for.
Okay, if somebody's not speaking and it's not the speaker, please keep your mics off. Any more people interested in talking to Jerry or making a comment or posing a question? Xingbao Zhao, please.
Hi, Jerry. I have another question. Maybe you already mentioned it in your talk. Sorry, I just missed it. So, so basically, you mentioned that the quantity you propose G as a function of delta Z, it has a close connection with the lattice QCD. So what is can you remind me what is the exact how to say the relation? So is this quantity easy to be calculated on the lattice?
Well, probably. We in physics should never say anything is easy. That's what I tell all my students.
Sorry.
What people have found, I'm showing this now on the slide. This whole new formalism, which is a new technique, and for calculating Q of X directly instead of using moments, I think is closely connected to allows a spatial connection between light front wave functions and what they calculate. The lattice calculates this matrix element.
Yeah, but this is a different thing, right? Still, because this in lattice Z is in 3 direction, not in the minus direction.
In the infinite momentum frame, if they can get to high enough P,
I see.
I think it becomes the same.
I see.
So that's why I said it's not easy, because well, first of all, I don't know how to do lattice calculations, so I never know if it's easy. But in principle, there's a connection if they can make the value of P large enough. Now you could see here what they would tend to say is that when you go from 6 to 8, this is the momentum in terms of inverse lattice units. You go from 6 pi to 8 pi, you go from you have a change, but then between 8 and between the red and the between the red and the green, there's less change. So they might argue that 10 pi is enough, and I don't think that's true. But sooner or later they'll get it. But so I think this is something that we can look at as a function of time and pretend that these calculations were done in the infinite momentum frame and compare wave functions. But it's important to compare at the same scale. The scale of the wave function defined in these universal wave functions of G and Stan and everybody else, that was I forget what it is now. It's about 0.1 GeV, and the lattice people have a different scale. But ultimately, I think one can correct for that and make honest comparisons between wave functions, and by calculating, I think this function H, I think is closely connected to G.
Okay, thank you. A related question is that if let's say it will take a while for lattice people to get it, let's say, to get it close to the light cone, is there any way for us to calculate let's say they are H, I mean, away from the light cone, from our light from the wave function. Do you
Yes,
think
I think that's a great idea. Yes, because you can say that you're predicting what they measure. I think it's terrific. Yeah.
So do you have an idea how to do that? If we have the light function.
Well, if you've got your light front wave functions, then you Fourier transform them to get them in Z space, and then calculate this G function.
But that needs some, let's say, that's not so trivial, right? Then let's say this correlation function would not be at the same time, at the same light front time. So in light front physics, we need to do some sort of time evolution in order to reach this kind of correlation function.
That I don't understand.
I mean because it's in order to get there, let's say H. In some sense, their H correspond to 2-point function which are off from the light cone. These 2-point functions are not light-like anymore. So that may, how to say, I mean, in my naive thinking,
yeah. Yeah, okay, that's something to think about, how close a connection it is.
Okay, thank you.
I think okay, on the let me think. If x plus is equal to 0, then x0 is minus x3, and x minus is minus 2x3. So I think there's some sort of connection in there.
I see.
I haven't worked it out, obviously.
Okay, thank you.
I'd like to ask a question related to the number of constituents.
Mm-hmm.
You have a model for distributions Q of X depending on the number of constituents tau.
Yes.
So in a real proton, different numbers tau would appear with different probabilities.
Correct. And they do.
Model displays some probability distribution in that number tau.
I agree.
Would one say that these probabilities of various numbers tau have something to do with probabilities of how many quarks or gluons there are in proton, or they are entirely unrelated to QCD?
No, they are related. I think, well, the people who wrote this paper should answer this. Chanbo and B and Stan and so on. But yes, in their model, which is meant to be a wave function at a certain scale, which I said somewhere in the talk, the mixture is about, if I remember correctly, if I don't remember correctly, you can look it up in the paper, it's 2/3 tau equal to 3 and 1/3 tau equal to 4. And the interesting thing to me is that they seem to be able to describe the data with only tau equal to 3 and 4. I would say, based on physics, I believe strongly that there's a pion cloud, and so there should be a 5 as well. But the model that they have, they get a good fit to the data with 3 or 4. A more complete description of QCD would involve more. And another issue is the lack of interference effects, that you only see things in terms of the squares of the wave function. So what they have is a model, but it's a very effective one. And but I think your physics point is exactly right. What they're saying is at a certain scale, you can get away with a 3-component model and a 4-component model. which I guess would be quarks and gluons. But you can, Guy will talk in a couple of weeks, and maybe he'll discuss this in more detail. But for me, it was just, a simple wave function to use, as you can see, so you could take Fourier transforms numerically and play this game of understanding the Z-tilde dependence.
I think this is an important issue, because lattice people would say that they are calculating their amplitude exactly as it comes out for a proton, while in modeling different components, we would have to argue that the different numbers tau are really coming out from QCD eigenvalue problem of some sort, instead of being just fitted to data.
Well, I would say this here, if you just read the paper, it's definitely a model. It's a holographic. It's based on a holographic model. It builds in a lot of different physics, but it's not. I would say, and has some remarkable features, but it's not QCD. But let's just say, for the moment, just for the sake of discussion, that this happens to be right. It's telling us that at a certain scale, you have only 3 and 4 constituents, and that's good enough to describe the proton wave function. And then the next step would be to try to go back and from this as information. It's like the answer in the back of the book. You go back from knowing that this has the right features to figure out, understand more deeply what is confinement. But I think you understand the issues very well, Stan.
Do we have any other voice to hear?
I raised my hand. Yeah, I'm not sure if that's.
I haven't
right
seen
method.
it, but yeah, go ahead.
Yeah, no. So, very interesting discussion, and so comment on the question of relating the lattice calculations to light cone PDFs. As I understand that this is, it's something like, it's easy in principle. It's, you take some limit to infinity, and then there's your answer. But in practice, it's not as easy.
Yeah, I said that, yeah.
Yeah, no, I'm not criticizing, but just to make, so recently we have started work on trying to quantify this. The thing about the lattice calculations is that the lattice, quote, observables, unquote, are very similar to, at least in structure, it's very similar to relating experimental observables to PDFs. Namely, the relation is through a convolution with a kernel that is exactly calculable up to some order. So the problem of extracting light cone PDFs from lattice is very similar to the problem of extracting light cone PDFs from experimental cross-sections using factorization.
Interesting. Yeah.
There's a factorization involved in both cases, and whether it's quasi PDFs or pseudo PDFs, Yoffe time distributions, or good lattice cross sections. The various constructions have been made.
Right.
The fundamental problem is the same. There's a convolution, and there's so. Last week we just posted a paper on the archive about this, and some early attempts to see in the context of simultaneous analysis of experimental cross sections and also lattice cross sections, quote unquote, what constraints we can get, on the light cone PDFs from both types of observables. So it's a non-trivial problem, and needs
I agree.
addressing.
Well, thank you for telling me about this. I missed this paper. School has started, or we start late at the UW, so I've been, I haven't read it, but now that I know that it exists, I'll take a look. Thank you, Wally.
Jerry,
Mm-hmm.
Steve.
Guy. Okay, Guy, go ahead.
Thank you, because I don't know if I raised my hand. It's just this very interesting question of Stan Glasek about the additional fog components, the cloud, if you want. That's a quite interesting question, because it can be quantified to some extent.
Oh, good.
So
Tell
recently, we put another PRL article for the unpolarized distributions, and how to relate them with the same parameters to the unpolarized ones. And there we saw that the higher fog components are quite important. However, when you take the limit x equal to 1, then you go back to valence, and they really become important. And we did again the exercise for the unpolarized ones, and we saw that the correction from higher fog components is very small, and that's why for the case of unpolarized, we have a good result in the paper mentioned by Jerry. But if you go to the unpolarized ones, then you must include them.
You mean you go to polarized ones, you have to include them?
If you go to polarized ones, you have to include them, yes.
Yeah, that makes sense to me. Again, I haven't seen the paper, but I'm glad you tell me about it. What I like to look at is D bar versus U bar. And U bar minus D bar is the signature in my mind of the pion cloud. So have you done anything?
I'm sorry, you mentioned D bar minus?
D bar minus U bar, or U bar
D bar minus U bar.
You see, if you have a pion cloud, then you get an effect. And I wonder if you were looking at
pointing. No, thank you for pointing this. Okay, thank you.
Good.
Let me jump in immediately and say that it would be interesting to see the distribution of gluons. What the candidate for gluon distribution would holography imply?
Oh, well, perhaps I can, if I have some results already, I can show some of them in my talk. But we're actually exploring this. And of course, this is very interesting, because in this case, the rigid trajectory in the formalism is the Pomeroy trajectory. And the results are quite encouraging, by the way. But this is just preliminary work.
Well, in 2 weeks, you will be able to tell us something about it.
Hopefully. Hopefully.
That's a homework assignment.
You cannot make plans for such a long time. Okay, perfect.
Okay, guys, it's very interesting discussion, and apparently we don't have enough time foreseen for the discussions that last much longer.
Perfect.
So the question is, if anybody wants to raise any point anymore. I see Philip. No, it's not. Anybody? Stan? I see you broadcast now on your camera. You wanted to say something?
I just apologize. I had my time screwed up. I thought it was 6:30 p.m., not 6:30 a.m. in the morning. So I just turned on. I just woke up.
You have a recording of the talk, I hope.
Okay, I will look at it.
It will be available on YouTube. unless something else is screwed up.
Hi, Stan.
I apologize for not understanding the time. I had it really at 6:30 p.m. Oh my God, it's really stupid. All right. But one thing about lattice I'll just remark is that, remember, lattice is not Minkowski space, it's Euclidean space.
Yeah.
And also, of course, it's frame dependent. So, you know, the results are not really the intrinsic results of a hadron. They're really very different. So, but on the other hand, the front form really captures the physics of a system, because it's the intrinsic time, intrinsic simultaneity. Everything about the front form is exactly the physics of the hadron, whereas the lattice is a construct. So
I think this new way of doing it has the potential, if they can get if they can get to large enough values of p, to make a connection.
Oh yes, of course you can go to the momentum frame, but there is a course. Yeah, there is a course other method.
They'll never get to the infinite momentum frame.
That's the problem. Yeah, exactly.
But maybe they can get close enough that we can.
Oh, certainly, but the front form. So, you know, also just. I think you probably talked about this, but you know, you can go back to discrete light cone quantization, basis light front quantization, and now there's quantum computers, and that's now starting to be on the horizon to really solve QCD exactly in terms of the front form. So this could be the new wave, and maybe James Berry wants to talk about that. But anyway, this is really a major advance, I think, to integrate quantum computing into the front form. So
good idea.
We'll see. Yeah.
There is a question of Xingbo Zhao about where your slides, Jerry, can be downloaded.
Okay. They're not on the web. I can. Let's see.
Well, I can suggest a simple way to you. If you mail the slides to me, or I will make them available to people on GC website. On
Right. Yeah. Yeah. Jinbao. Yes. Okay. I can. I'll mail it to you, and I'll also mail to Jinbao. He seems to have emailed me during the talk.
Yeah, and I hope, Jerry, you noticed the reference from Wally. When the GC broadcasting stops, the comment will disappear. So take a look at the arXiv number that Wally displayed.
I sent an email as well.
Oh, I see. Thank you.
See it, Wally. Anyway, I'm sure it'll get here sooner or later.
Anyway, now it's already past 5, so the question is if anybody really needs to add something, or there's no more volunteers to speak. I will count to 5.
It's amazing that there are still 41 people here, apparently.
All right. So nobody raises their hands. So I thank you very much for participating in this first seminar. Thank you, Jerry, for very interesting first opening. And we are looking forward to a meeting in 2 weeks when Guy Determant will illuminate our comprehension of holographic approach to QCD. Thank you very much for participating, and see you in next 2 weeks. Bye-bye.
Thank you, everybody. Bye-bye.
Bye. Thanks, everybody, for your questions.
Thank you. Bye.
Thank you so much. Bye-bye.
Jerry, one last thing. I apologize for missing the talk. I'll watch it when it's replayed. But I just woke up in the morning. I didn't realize that that
yeah, that's all right.
I really thought it was 6:30 p.m. tonight.
I think
I really
got it totally. It's reasonable. I mean, this is really crazy. I never in my life gave a physics talk at 6:30 in the morning.
Right. It sounds like you did a terrific job on it. It's very good, really terrific.
Thank you. Yeah.
But,
giving a talk at 6:30 in the morning to 70 some people.
Yeah.
There were 70 there. Oh, good. I didn't realize there were that many.
Yeah, we still have people present.
There's still 13 who haven't logged out anyway.
Okay.
I had fun. It's a good thing. I'm glad I did it. I meant to say this during the talk, but I didn't. That I followed your suggestion that we focus on one subject rather than talk a lot of stuff. I think it led to more constructive discussions because people could find out. When people, a lot of these Zoom type talks, people talk about their entire career almost, and each slide discusses 3 papers, and so the whole talk here was devoted to 1 paper. So it's an old-fashioned seminar.
Mm-hmm. By the way, I don't know if you know, but Gita Terman just won an award from Wolfram Foundation on light fun. Yeah, holography. So that's great. Yeah.
That's wonderful.
Yeah. I should have said that while you were still on. I'm sorry.
Yeah, I didn't know that. That's great.
Yeah. So our field's being recognized. This is really good, and it's really it's so superior to everything else that you can imagine. I mean, it's really, really the right way to do physics. Not a question about it.
Okay, so I need to play this very frustrating role of a chairman who needs to close the seminar.
Right. Thank you. Thank you, Stan.
Continue talking. I hope later a code for really opening such discussions and making them a habit in the spirit of discussing one good paper instead of the entire career curriculum. Okay, thank you very much, and I'm turning off the broadcast.
Thank you. Thank you, Stan. Bye.
Bye.